And so we will have another day to review area volume. But this is a very common FRQ on the AB portion of the AP exam. So I want to make sure that we go over it. And eventually we will have a quiz over this topic after the break. But just wanted to start using this list. So at the very top is just reminders of units of measure. Anytime we are finding the derivative or rate of change, we're always dividing, right? And the fact that we're dividing, that means we're going to add another time component to our denominator. But if we are taking the antiderivative, we're always multiplying units together. And because that multiplying of units, it's going to end up stripping away that denominator. So if I have miles per hour, antiderivative will take me up to miles. But if I want to find the rate of change of something that is in meters per second, I going to get down to acceleration, so meters per second squared. I think we tend to be pretty good with derivatives and understanding, oh, I'm going to be tacking on another time component in the denominator. But we just need to be reminded that when you go through antiderivative, we're multiplying units and your units will change, but typically that time component will get stripped away. Okay, so these are what they categorize as rate in, rate out. So both, there's usually two functions, and one function is dealing with the rate at which something is inserting or coming in. And then there's another rate function that is telling us how fast something is leaving. Right. So, but the important thing is that these are usually going to be given as rates. So let's see, the rate at which people enter an amusement park on a given day is modeled by the function E, defined by E of t. The rate at which people leave the same unit amusement park is modeled by the function L of t. Right? Both E of t and L of t are measured in people per hour. That's important here, people per hour. And the time is measured in hours after midnight. These functions are valid between 9 and 23. So 9 a.m. and 11 p.m. This is a military time here. The hours in which the park is open. At time t equals 9, there are no people in the park because that's when the doors or when the gates open. So part A, how many people have entered the park by 5 p.m.? So if we have the rate at which people are entering into the park, how can we use this to find the total number of people who've entered the park? Take the what? How can we get people per hour up to the number of people? Antiderivative, yeah. So we're going to accumulate that rate over the time period. So an easy example would be, okay, if there's 200 people coming in per hour, then I'm going to multiply that 200 per hour by, however many hours have passed. But now this is kind of like a variable rate, but it's the same idea that we're going to keep accumulating that rate over our total number of hours, and that's going to give us the number of people. Okay, so we're going to take the depth integral from 9 to 17. 17 is 5 p.m. So over the course of that 8-hour period, we're going to accumulate that rate. So E of t is in terms of people per hour. Time is in terms of hours. So people per hour times hour, we're going to get the number of people who've entered the park. So we're going to practice inserting this into our calculator. So we'll let y1 hold E of t. T is in your is on paper, but you're going to use variable x in your calculator. Math 9. So this tells us that over the course of that 8-hour period, 6,004 people will have entered the park. Just save some room here. I'll put B up here. Part B, the price of admission to the park is $15 until 5 p.m. After 5 p.m., the price of admission to the park is $11. How much money is collected from admissions to the park on a given day? Round your answer to the nearest whole number. So why don't we figure out a way to count the number of people who will get charged by that full admission price, and then also count the number of people who are going to be charged the $11. So we already have some of the information, right? The 6,004 people are going to get charged what? $15, okay. And then what can we do to find the number of people who is going to be charged at the cheaper rate? Yeah, 17 to 23. Good. All right, so we already have part of it. Take that 6,004, multiply by 15, and then we can find the number of people. After 5 p.m., find that number and multiply it by 11. That'll get us to the total amount that the park is going to collect through admissions. So 15 times 6,004 and 11 times whatever this number is. Okay, so try that, see if you can confirm the answer that I got. All right, any questions with part B? Did everybody confirm in their calculator? All right, part C. Let h of t be equal to the integral from 9 to t of e of x minus L of x dx. So they say that the value of h of 17 is 3725. So I'm just going to see what that looks like. So h of 17 is equal to the integral from 9 to 17 of e of x minus L of x dx. And they tell us that this number is equal to 3725. Okay, can we interpret what this is saying? So the integral of e of x, that's going to give us a number of people who've entered the park. What is the integral of L of x going to tell us? Okay, who've left the park. So what do you think e of x minus L of x integral is going to, what do you think this number means? Yeah, left in the park, right? So we take the number of people who've entered the park, and then we subtract out the number of people who've left the park, and the number that we see is the number of people left inside the park, right? Number of people remaining in the park at this time, 5 p.m. Okay, so it says explain the meaning of h of 17. So h of 17 means hey, are we good with that? There's also a second part to this problem. It says, explain the meaning of h prime of 17. Okay, so let's build up to that. Before we do h prime of 17, let's do h prime of t. So h prime of t is asking for the derivative of this. So let me just put that in derivative notation and see if we can interpret what that is telling us. So h of t is the integral of v of x minus L of x. So h prime of t must be the derivative of the integral of v of x minus L of x, right? So are we in agreement there? Now, what does this remind you of whenever you see this notation? Second theorem, right? So this, we see two opposite operations on top of the same expression. How can we clean this up? What would this essentially mean here? We know these operations cancel out. We just have to worry about what? Yeah, the t gets inserted, multiplied by the upper bound's derivative, which is just times 1. So really, it ends up being e of t minus L of t. Are we good with building h prime and cleaning up h prime and looking at what h prime is equal to? Okay, let's spend a minute talking about what this means, right? So E of t is the rate at which people are entering in the park. L of t is the rate at which people are leaving the park. Okay. How is this number going to fluctuate over the course of, let's say, a normal day at like Six Flags? Which is going to be greater at the beginning of the day? E of t or L of t? E of t, right? There's a lot more people coming in at 10 a.m. than people who are leaving at 10 a.m., right? So probably very few people. So E of t minus L of t at the beginning of the day is going to end up positive or negative. Positive, right? You have a lot more. The rate of people entering in is going to be a lot higher than people are leaving. What's going to happen towards the end of the day? It's going to be opposite, right? More people. There's less people coming in at 6 p.m. than people who are leaving at 6 p.m. Right? Let's say just like a normal day. Okay, so let's see here. H prime of 17. It says explain the meaning of H of 17 and H prime of 17, and then find the value of H prime of 17. So let's do that. H prime of 17 is simply E of 17 minus L of 17. Right? And we're expecting this probably to be a negative number because at 5 p.m., we expect the rate at which people are leaving the park to be higher than the rate at which people are entering in the park. Okay, so let's test that out. Right now, I have y1 being E of t. I'm going to let y2 be L of t. And you're only using x's in your calculator. So if I do alpha trace, I can just do y1 of 17 minus alpha trace, y2 of 17. I got negative 380.281. So what does this mean? Negative 380 people per hour. Yeah. Yeah, rate at which people are leaving, or rate at which the park is shrinking, right? Number of people is decreasing at a rate of 300 people per hour in the park. Yeah. All right. Part D. At what time between 9 and 23 does the model predict that the number of people in the park is at a maximum? So if you had to guess, let's say it's a normal day on the at an amusement park, what time of the day, around what time of the day would you expect there to be the most number of people in the park? Yeah, well, probably like sometime mid-afternoon-ish, right? That's when, when the most number of people are in the park before people start leaving, right? So somewhere in that mid-afternoon. So the way that we can find the maximum number of people is we can think about what's happening with EFT and LFT, right? So over the course of the day, EFT is going to start off high, LFT is going to start off low, right? And in general, what's going to happen is it's going to start doing this, right? EFT is going to start high, it's going to start decreasing. LFT is going to start low and increasing, but eventually they're going to meet, right? And after that point, LFT is going to start rising, right? So we want to look for when is EFT and LFT going to be equal, because when they're equal, that is right before when the park starts to decrease in size. So we basically can look for when is that H prime equal to what? 0, right? That is going to be where our maximum is going to be, because if EFT, and as long as EFT is higher than LFT, the park is going to continue to increase in size, right? But then as soon as LFT overtakes EFT, then the park begins to shrink, right? As soon as there's more people leaving the park than people entering, then the park size is going to begin to shrink. So the maximum is going to occur when H prime is equal to 0, when EFT and LFT are equal to each other. So we basically want to set H prime equal to 0. So since H prime is EFT minus LFT, we can do this. EFT minus LFT is equal to 0. Now, we could do this. We could plug both EFT and LFT into the calculator and see where they intersect. Okay. But I think the better strategy is graphing this and then look for the what? Yeah, look for the x-intercept. I would prefer this way, because if you do EFT equals LFT, that works too. But the thing is, these numbers are so big that it may take some time for you to search across the first quadrant to see where they're going to intersect, right? Especially if the numbers are in the thousands. I think what's easier is you graph EFT minus LFT, and then just focus on where that graph is going to hit the x-axis, right? It's a little bit easier to go searching along the x-axis than go searching where the two graphs are going to intersect. And also, we know that the t-value that we're looking for is going to have to be somewhere between 9 and 23, right? So we have a very easy place to look for our solutions rather than searching all over the place. Okay, so I'm going to do this here. Rather than retyping my EFT and LFT, I'm just going to use Y3 to graph what I want to see. So E of X is stored under Y1, so I'll do Y1 minus Y2. But I don't want to see all these graphs. It's just too much here. So I'm going to scroll to where my equal sign is, hit enter. Then you're going to see the equal sign unhighlighted. So we can still access it, but it's not going to show up on our graph. So we just want to see Y1 minus Y2. We just want to see EFT minus LFT to see where it crosses the x-axis. Now I'm going to play with the window a little bit, because these numbers are in the thousands. So we want to zoom out so that it doesn't look like a straight line. Otherwise, or a vertical line. We want to have some perspective here. So now my x-min, x-max, I know that we're just looking at between 9 and 23. So I can just say 9 to 23 here under Windows. And then Y min, Y max. If you look at our functions here, our functions are in the 15,000s, almost 10,000s. So I'm going to say, I don't know, I'm just going to say negative 1,000 to 1,000. I can always come back and adjust my Y min, Y max if it's not showing, if I'm not seeing a nice curve for me to trace and find that x-intercept. Let's just see what where this gets me here. So x min, x max 9 and 23, Y min, Y max negative 1,000 to 1,000. Let's see if that will give me a good graph. Okay, so it's pretty good, right? That's it's easy for us to look for that x-intercept. This is what we're looking for, and we're expecting some time in the mid-afternoon for when the park is going to be at the maximum. So second trace, we select our 0, pick a point to the left of the x-intercept, hit enter. Pick a point to the right of the x-intercept, hit enter a third time. 15.79. That's around like 3 p.m.-ish, right? Okay, let's turn to page 3. I want us to do one more of these problems. Okay, part A. This is number 3 here. Okay, the tide removes sand from Sandy Point Beach at a rate modeled by R of t, always in radian mode, our calculator should be. A pumping station adds sand to the beach at a rate modeled by S of t, 15t over 1 plus 3t. Both R of t and S of t have units of cubic yards per hour. At time t equals 0, the beach contains 2,500 cubic yards of sand. So we have a rate at which sand is being removed by the tide, and then we also have a rate at which sand is being added to the beach by a pumping station. So part A says, how much sand will the tide remove? So we only care about removal here from the beach during this 6-hour period. So we have the rate at which sand is being removed at cubic yards per hour. So what can we do to use this and find the total number of sand removed? Take the integral. Good. So the integral from 0 to 6, accumulate that rate over a 6-hour period, and we're going to be able to convert that cubic yards per hour to to cubic yards. All right. So in your calculator, type in 2 plus 5 sine. Uh, 4 pi x over 25. Math 9. So 31.816 cubic yards of sand. So see if you guys can confirm that number in your calculator. Part B, write an expression for y of t, which represents the total amount of sand on the beach at any given time. So this is going to be a formula that is going to be common amongst these rate in, rate outs problems. So I'm going to have us write out this formula and we can revisit it across different problems. So here's the general formula that we're going to see here. The total amount at any given time has three components. We want to know how much there is to begin with, initial amount. Sometimes they could be zero, but we always want to consider that they're plus the amount added minus the amount removed. So that's going to be the general formula for a lot of these rate in, rate out problems. If I want to figure out how much there is at any moment in time, I need to involve three components. How much is there to begin with, how much has been added, and then how much has been removed. If I combine those numbers together, I'm going to be able to figure out how much there is at a given time. So I'm going to use y of t to represent the cubic yards or the amount of sand at any given time. Y of t is equal to initial amount. What can we say there? Okay, 2,500. Okay, the amount added is going to involve what? Integral of S of t. Now, we want to give it that flexibility so that we can find, using later formulas, we use formula where we can adapt it for any moment in time, right? Either 2 hours in or 3 hours in or 4 hours in. So I want to use the integral notation, but give it that flexibility. So I'm going to say from 0 to t of S of t. But usually what we do is if there's a variable here, we want to use a different variable so it can get plugged into that variable. So S of x is the same thing as S of t. It's just that when that t gets inserted, it turns into S of t. So whenever you want to create a formula where there's a bound being a variable, just make sure that you're using a different variable down here. Usually, if it's t and then x. Okay. Minus the amount removed, same setup here. We're going to accumulate the rate of the tide removing the sand over a period of time. So from 0 to t of r of x dx. Okay, so we have that flexibility. If I want to find the amount of sand at 2 hours, I can use plug 2 in and then get that number and add these together. If I want to find the amount of sand at 5 hours, I can plug that number in, right? So we have a flexibility to find the amount of sand at any moment in time. Okay, any questions with this? Okay, so that's all part B is doing. But a lot of times, free response questions, you're going to see how they're kind of helping you build enough information so that when you get to that last part, you have the setup required to answer these questions, because we're going to use this formula down the road when it's asking about max and min. So they're kind of building that information up for us. Okay, for part C, find the rate at which the total amount of sand is changing at time t equals 4. So find the rate, okay, find the rate. What unit do we want to end up with for part C? We want to go back to what? Cubic yards per hour, right? So if I have something that is in terms of cubic yards, I got to do what to get it down to cubic yards per hour? Find the what? Derivative, yeah. So we have this function, and then for that function, we can build the derivative for solving part C. So we want to get it down to y prime of t. We want to find out the rate. We want to basically find y prime of 4. But let's find y prime of t first. 2,500 turns into what? To 0, okay. Here, I want to find the derivative of this notation. So let me just write out what I want to do. I want to find the derivative of this mess minus the derivative of this mess and this should clean up pretty nicely here. So basically, what can I say y prime of t is equal to? This becomes just what? S of, yeah, the plug, yeah, t gets plugged in, yeah, S of t, okay, minus R of t, right? We're just applying second theorem here. We're able to get it all cleaned up. So y prime is simply S of t minus R of t. Now, if I want to find y prime of 4, I can just insert into my formula. So I have R of t in my calculator. I'll plug in S sub t in my calculator as well. And then I'll just make my calculator evaluate those values for me. So I have S of t stored under my y5 in my calculator. And then I have R stored under y4. So wherever you have it stored under, you can just evaluate it. Okay, negative 1.908. What's happening to the sand on the beach at 4 hours? Right. So overall, even with the pumping station adding sand, the beach is still losing sand at this moment in time because the tide is pulling more sand away than sand getting pumped in. Yes, question.
If the graphic public graphic, it's not something that came as kind of graphic.
Yeah. You see, there's equal signs. If you go and if you hit and enter on that equal sign and unhighlight the equal sign, it will no longer graph it.
I can't get out of like it's equal when you do anything while it's
Did the on button.
Yeah, sometimes I just turn the calculator off and then turn it back on again. Okay, part D. Now, this is an important problem here because typically with these rate in, rate out problems, they always end with something about finding max and min. So there's always like this extreme value theorem portion that's built into these rate in, rate out problems. So for part D here, at what time is the amount of sand at a minimum? So we basically are looking for absolute max, absolute min, or in this case, absolute minimum. This is applying extreme value theorem. So to apply extreme value theorem, what do we have to make sure we test? What are our candidates? Critical points and endpoints. All right. So endpoints are easy. We are going to consider the amount of sand at 0 hour. We're going to consider amount of sand at 6 hour. And then we're also going to find critical points. So critical points is where the derivative is what? Equal to 0, right? So we just need to find that time when the derivative is equal to 0, and then test our endpoints, and then we insert them all into the y of t equation to figure out the amount of sand at 0 hour, 6 hours, and whatever we find from y prime. Okay, so let's find critical points first. So just like before, we're going to graph S of t minus R of t, and then simply look for the x-intercept. So I have my S of t stored under y5. I have my R of t stored under y4. So I just want to graph y5 minus y4. That's what I have in my calculator. And then I want to adjust my window. I only care about my time values between 0 and 6. I look at my equation here. I don't need to be in the thousands here, so maybe I'll just go from, I don't know, -10 to 10. And if that's not good enough, I can always adjust the window later on. I'm just looking for the x-intercept. So it looks like it's around 5 something. So look for my 0. .117. That's the only x-intercept that I have. So I'm going to test the critical point and the endpoints, 0 and 6, and they all get inserted into my y of t equation. And whatever is the lowest is going to be my absolute minimum. Now, y of 0 is easy because we already know that there's only 2,500 cubic yards of sand to begin with. Okay, all this gets inserted into our calculator here. So the absolute minimum amount of sand is 2492. Because after comparing my candidates, 2492 is the lowest amongst these endpoints and critical points. Okay, no homework. Just want you guys to use the weekend to begin looking and studying for your Tuesday quiz. And then Monday, we'll have another day to do a quiz review. I'll also have a help session Monday, but it'll only be a half session because I'm me at 7:45. So I'll have a help session at 7:15 to 7:45, going over the morning review in your quiz review work. All right, folks.
Well, actually, it's July. Yeah. Okay. I thought you said something. I do want to see it. Thank you for that. Actually,
Yeah. I do.
yeah.